So last time we saw about visualization and exploration, right? One of the key, we are still in the explore section of the data science, the fundamentals of data science, where we are trying to explore to see how the data looks and things like that. So the first thing would be to visualize, to make some pretty pictures to see if the data makes sense. Did anybody try the exercises in there? No? Okay. But today there's not going to be too much of any homework exercises. Okay, so what we are going to do is we are going to do the exploratory data analysis on Thursday and next Tuesday, and then you're going to submit that as a homework. Okay, so I didn't make too much of homeworks in this one except for a couple, which should be pretty easy. So another key aspect of doing data science is transformation and exploration of data. Okay, so let's get it started. We will work with the same Haynes data set. Okay, in the spirit of data transformation, we will look into what is known as a deep layer function. Okay, so the deep layer function is a part of the tidyverse, and it facilitates lots of functions that are useful for data transformations. And transformations are critical when you do when you're working with the data. Okay, so let's first, as usual, import the curated Haynes data set. Okay, you have this data set. So I'm calling directly from the website, right? You have the URL link here. And as usual, when you import the data set, the first few of them are should be categorical, but they have been named as numerical. So we change them, the gender as a factor, age group as a factor, health status, and the diabetes status as factors. Okay, so we are transforming that. And then we are omitting the NA values that are missing values, and then we are looking into the data set to see it's all fine. Okay, so looks good, right? I mean, one of the things that I want you to do in your homework or in your project is to make it more readable. Okay, so it's not like, okay, I do this and then I turn it into a homework, right? I mean, you make it more communicative, you make it more attractive, you put in figures and you explain. So those things are also will be considered and for your finals. So make sure when you submit the homework, just don't give a one-line code. Even if it is a one-line code, try to emphasize what's being done there. So I do that for all the examples. I put a comment line to say that what it's actually doing. So I would want you to follow such best practices, okay, when writing codes. So here, so we are looking at the data set, and this is the first principles. Once you load the data set, you take a look at it and see if everything is okay. So far, fine. Okay. One of the things that you might have encountered so far when we are working with our examples or the homework is that you would have gotten tons and tons of lines when you are printing out a data set. For instance, Haynes, right? You are printing it out. When you type in Haynes, you are going to get tons and tons of lines in your R Markdown file or what you see, right? So to make it more easily accessible for people to take a look at the data, they have developed what is known as a tibble. Okay, a tibble is nothing more than a data frame. It is kind of a data frame, but it is something that you can easily look at the data. So that is it's a table, but it's a table nicely formatted for you to have a good visualization. So tibbles are data frames that are, in fact, they do less than data frames. They don't really do more things, and they in fact combine more when the variable does not exist. So it's good to have such a shorter a version of a data frame, because you can confront problems earlier than going over all this complicated analysis just to find that you have some problems. And they also have an enhanced print method that makes easier to use with complex objects. So we will see what it is now. So to convert a data frame into tibble, we can use the function as tibble df, where df is a data frame. Okay, so we will convert Haynes data frame into a tibble and use tibbles from now on. Okay, so what I'm trying to do is I'm trying to load a library, tidyverse here, which is the critical library that we will be using throughout the course. and I'm converting this Haynes table, Haynes data frame into a table. Okay, so once you make it into a table, you will see that it has condensed several information, and then it's just going to give you a small table containing what the main aspects of the data, right? I mean, unlike if you print out a Haynes, you're going to have all the, or at least 1,000 lines or something. It's going to print crazy number of lines. So tables don't give you that. Tables give you a short table, short summary of what it is. So whenever you are submitting your data, first convert it into a table, work with it, and submit it like that in a table format. So you don't really, go into pages and pages of HTML file. Okay. All right. So that's the first thing. Once you convert into table, okay, there are six basic functions that allows data manipulation. Okay. The first is a filter. You may want to filter out certain values. You may want to extract, say, all people who have diabetes, something like that. Okay. The second is order. You may want to order, right? I mean, you want to rearrange the rows. So that's given by the order function. And there is another function called select. The select is similar to filter. In filter, you choose rows. In select, you choose columns. Okay, so that's the main idea behind select, difference between select and filter. And you can create new variables. You may also want to often create new variables to see how the data is transformed, right? Or creating something like, when you have time and let's say that you have distance, you may want to compute speed by saying speed is distance by time, right? It's a new variable. And you may want to use summarize, and that's given through mutate. Okay, so all these functions work with what is known as a summarize, and summarize actually it's one of the most useful function. It's coupled with what is known as a group by. Group by is something that you can categorize. We will come to group by operation. It's one of the most useful operation that you can ever imagine when you're doing data science. Okay, so oftentimes you may want to group, like for instance, when you're working with the gene expression data, right? You may want to select all genes in a certain pathway. So you use a group by on a pathway, and you will get all the genes in that pathway and do some analysis on it, right? So that's an example of a group by. We will see some of these examples in detail today. Okay. So let's go over the filter function. This is an example. The filter function allows to pick a subset of information from the data set. Like for instance, in our Haynes data set, I want to choose, let's say, all patients between age 45. Okay. So what you do is a simple filter. You apply a filter with a Haynes data set in there, and there's age given by the SP age variable with 45, and then I want to choose with the HDL value of 50. So it's simple, right? I mean, so it's not too complicated, and it's going to print out just in the table format of all the patients. Actually, it's not going to be a table format. All these will be a data frame. It will give you this format of the patients who have who are in the age of 45 and have a HDL value of 50. Now, all deploy functions write the result to a new data frame. Okay, so if we want to store the data, we need assign the variable result to a variable. So you can assign this variable or some variable to all these functions that we are talking about. Okay, and we can also use comparison and logical operators. So for instance, here I want to find out all patients who are between 45 and 46 and the HDL value of 50. You can directly use the comparison operator here. Age is greater than 45 and age is less than 46, and then who have the HDL value of 50. And so you see that there is a value that's there's a table that will list all records for patients between 45 and 46 with a HDL value of 50. Okay. Now, filter only includes rows where the condition is true. Okay, so it excludes both false and missing values. It's going to exclude that. Okay, so this is a simple homework. It's not too much. So find all patients from the Haynes data set who are females and in between ages 45 and 60 and who are in excellent or good health status, who have diabetes but are not yet diagnosed, right? Have total cholesterol between 140 and 200. So these are very simple exercises that you can try with this data set. And you are welcome to try this with your own data set as well. Choose something that works on your data set. Arrange function. So similar to what filter does, arrange is similar except that instead of selecting rows, it changes the order. Okay, so it takes a data frame and a column names, a set of columns, and how to order that column. Okay, so if we provide more than one column name, each additional column will be used to break the ties in the values of the preceding. So for instance, let's look at this example. Haynes, I'm arranging by gender, age, and the descending order of creatinine in the urine. So it's Haynes gender. So what it can do is it can sort, right? I mean, these are the functions that's provided by arrange. And so I do this and then I query for it. And then you see that it's sorted by the creatinine content is starting with 612 to 217. It's arranged in the descending order. Okay, so DES is a descending order function that you can use within these deployer functions, okay, to look into that. Missing values are always sorted at the end when using arrange. And to view the last few entries, one can use the tail function. This could be a very important function to use, tail. So if you query for tail of the table, it's going to give you what's there in the tail of this. So it's 73, etc., etc. Okay, so it's an important function that we made. The homework: sort Haynes to find patients with highest cholesterol. Do the same to find patients with least cholesterol. Sort Haynes to find patients with high A1C. Okay. Next, we are coming to one of the important functions called the select. Okay, so if anybody looked into the original data set Haynes, or did you all use the curated ones? The original has 704 variables. Okay, and this is how in general the data sets are going to be. If you look at the Mimic 3, it's crazy, right? I mean, there are so much of data variables in here. So the select would allow us to include only the variables of interest. So for instance, here is a code just to take the A1C and glucose. So it's very simple. Select the data set name, A1C and glucose, the hemoglobin content and the glucose, and you show it as a table, right? So you will see that it extracts only the columns. Okay. So another useful helper argument is everything function that can be used in combined with the select function that will keep all the variables outside and it will just push the variables of interest in the front. So for instance, if I say Haynes, A1C and glucose and everything function here, it's just going to give me the table or a table with the first one as A1C and glucose. The rest of them it's going to push back away from it. So when manipulating large data sets, you may want to use this. Okay. All right, let's come to the mutate function. So we can add new columns to the data set using the mutate function. Okay, so for example, this code makes a new variable that's a sum of HDL, the high density lipo, and also LDL estimate. Okay, so it stores it into a new variable, and we can find the ratio between cholesterol and new variable. So that's what the mutate, it makes a new variable. So what I'm doing here is I am selecting only a subset of variables. I mean, I really don't need some of them. This step is not necessary if you don't want it, but I'm just selecting the Haynes, LDL estimate, HDL, cholesterol, and triglycerides, and then I'm mutating the data, right? And I'm forming a new variable called H_L that is a sum of HDL and LDL estimate. And once I do this, I can find the ratio of this by saying cholesterol divided by H_L, right? It's going to give me this ratio. and then I want to see how it looks like. So it immediately forms this new, and it's going to give me the ratio of this. Okay, so what so far I'm doing is giving you the pieces of puzzle. Okay, I'm giving you Lego pieces, so you have to make, using all these things, you have to make a good interpretation of the data that you're working. Okay, so these are important functions. It's to form a new variable. You can form a new variable that makes sense for your data set, right? So for instance, if you just want to keep the new variable instead of all the variables, you can use the transmute function. Okay, so the transmute function just keeps the newly created variables and it throws away the rest. Okay, so it forms a tibble and just keeps this. Otherwise, you can use what? You can use a select right along with that. So it's fine. And there are several other useful functions for data manipulation, such as lag, lead, cumulative sum, minimum rank, etc. And these are some of the things that there are wrappers around them. So for instance, top n is a function that is made of filter and minimum rank. Okay, that would list the top n values of the data. So for instance, if you want to look at the top 5 values of the data, you put top underscore n, the data set, how many you want to extract from it, and the ratio. Okay, so you can immediately see that it's going to give you the top values. Okay. Now we are coming to the most important part of data analysis, which is group by and summarize function. Okay. So group by is an extremely useful function that facilitates grouped analysis along with summarize, and they can provide vital statistics, right? Summarize can be used to provide vital statistics. So this is a question now. Let's say that we want to find the mean cholesterol level for each gender. Okay. The group by and summarize can be really, really handy. So what this code does is this. First, this is going to take this Haynes data set. It is going to group by gender. So it's going to take males separately. It's going to consider females separately. And you are trying to find the mean cholesterol by this summarize function. So you're using this data set and you're trying to find the mean cholesterol levels. Okay. So it's not going to consider everything together now. Since you're already grouping by, it's going to provide statistics only for males and females. Okay. So this is a very important thing that you may want to explore groups in your data, especially if you are having some categorical variables. It will be really handy to find what are all the things of interest happening within a particular group or category, right? So we find the mean cholesterol levels for females are a little higher than males, right? I mean, so if you look at it, it's 187 and 183, I mean, which is interesting. And the summarize has one another useful function called the count that will count the number of items appearing in a group. So for instance, here is an analysis that shows the relationship between HDL and LDL for each group, for each age grouped by the number of patients for that particular group. Okay, so what we are trying to do is group by Haynes and Spades, or the SP8s, right? So what does this mean? So think about it. Age is a numerical variable, right? We are now not grouping by the category. It's not necessary that you have to categorize only by the categorical variable, but you can use it categorize using the age variable. Okay. Now you can summarize by the number of people in that age. So the count is going to give you the number of people in that age. Okay, and I can try to find the mean of HDL and LDL estimate for that group. Okay, now since there are about 1500 records, there will be lots of people right in each of these groups, and so I want to exclude some of them. So exclude all these ones that are less than 5. Like, let's say that you can do this with the same gene expression data, right? I mean, you may want to see how many genes are in a pathway and find the mean expression of the genes. And then there could be some noise that you can always remove. So this is what the filter actually, I'm using the filter here to remove the noise, right? And then what we can do is you can do a plot of this data set, right, with The x-axis is the mean HDL estimate, y-axis is the LDL estimate, and we can smooth it, right? So what does this SE equals false do? It was given in the last homework. Anybody remember? Did anybody try? Yeah, so that gives you the confidence interval, right? So if you're setting it true, it's going to give you the confidence interval. So this is the graph that you get. So all these things, right, are count. So all the small one is a count of 10, this is count of 15, etc., etc. So all these people represent the number of groups, people in that, and this is a HDL, mean HDL and the mean LDL, and you can smooth it, right? So the big disadvantage in this code is, like, if you have to see that it's all, once you type in Haynes here, and if you're finding H, you have to supply again and again, right? You're using two functions here. So for instance, DL, right? These two can be combined. All these operations can be combined by a versatile symbol. You have a percentage, the greater than, and the percentage symbol, okay? This is called a piping. Have anybody done Unix here? You know piping, right? So you put one output to the other. So you can build a pipeline using this symbol, okay? So this is a piping. So for instance, the same thing could be done like this. You have a Haynes data set. I input the Haynes, the output of the into piping, and then I group by age, and then I pipe, and then I call summarize, and then again I pipe the result to filter. So the analysis is going to flow in this direction, and then write it here. So as soon as it reaches this pipe, it says that the data goes from one to the other. So it's going to go on this direction, okay? Now I can plot it. You're going to get the same result no matter what, right? You're just inputting. So pipe can be a very, very handy tool. Like if you're building complicated analysis, you can just keep the pipe symbol and keep going on, okay? And another important function is the use of na.rm, so missing values. It will remove the missing values inside the summarize. So let's say, since we already removed the na from missing data from our data set, we will import it into the new data set, okay? So what we are trying to do here is actually making the new data. It's just the same data set without na removed. So it's called, I'm calling it as Haynes with na, okay, with the missing values here. Now, without removing na, if I try to group by age and gender and summarize the mean cholesterol, you get this. There are several missing values here, right? So you get lots of na. But instead, what I can do is I can remove the missing values by saying na.rm equals true inside the summarize, okay? Inside the mean. In fact, the mean has this argument called na.rm. All these can be checked by question mark in your R console, okay? So once you do that, you'll see that it had removed all the na values and it gives you only the numbers in here, right? So that's an important function to make use of. And also we can filter through the missing values. So instead of just removing it, you can initially filter it. So what I'm trying to do is I'm trying to take this data set, piping to filter, to remove cholesterol total, and then grouping by age and gender and showing the mean. It's going to print out the same, okay? But instead of doing it, instead of removing, I'm just filtering. I'm using the filter SNA. We already saw this in our first couple of lectures, right? You can use that. So whenever we do aggregations using group by, it is good to include count information that will give an information on the distribution and extreme values. So for instance, here you have a cholesterol. I am grouping by age and gender and summarizing, right? And what we can see how this varies as a count. You can see the distribution of the data, right? So I'm plotting the mean cholesterol here with the count. So it's going to show me how the frequency distribution of it. So this can be useful because you can find that there are at least some people who have very high cholesterol content, the more than 300 or so, right? So it's always whenever you do this aggregation, you include the count information in there, which can be plotted. So how does cholesterol vary over the age group, right? We can get more insight if we can draw the ratio between HDL and LDL for each group. So for instance, what I'm trying to do here is I'm trying to find the ratio, right, of the HDL and LDL, right? And I'm plotting this information, giving it to X and Y and plotting it, this information, right? But for the age group, I'm trying to, and then you see that there is for the age group 20 and 39, the cholesterol level is almost negligible. I mean, it's about 70s, I think, or 170s, and then it shoots up here and then to here. So these kinds of information, right? The cholesterol peaks at for age group 40 to 49 and remains almost stable. Okay, so these are some of the things that you may want to explore and find out, and these are the functions group by can be extremely handy, right? This is a very practical question that you may want to ask, right? How does the cholesterol vary over the age group, right? I mean, you have a age group cat, or how does the cholesterol vary over people who have diabetes and people who don't have, and people who have diabetes but not yet diagnosed, right? So, and also there are several useful summary functions. For instance, find the mean of cholesterol total and the mean of cholesterol if the glucose is greater than 100 for each age group. This is a query, right? So for Haynes, I'm piping it to group by because I want it for each age group, right? So you're grouping by the age group and you're trying to find the mean of cholesterol total and the mean of cholesterol total where the glucose is greater than 100. Okay, so this is a query that you have to form, and once you form that query, it's going to spit out the answer for each age group, right? It's going to give you the glucose and the cholesterol content, and the cholesterol content where the glucose is more than 100, right? So it's going to, you can see immediately the difference, how it varies. So for instance, it's 176 and 182. So people who have glucose greater than 100 have higher cholesterol, right? So this kind of information that you can query and find out. Find the standard deviation of cholesterol by age group. So SD is a function that you can use to find the standard deviation in the data. So you're grouping by the age, summarizing and finding out the standard deviation and arranging the data in a descending order. So you have the age group. So you can see that standard deviation for each age group. Find the largest and smallest cholesterol for each diabetes diagnosis group. So you have group by the diagnosis group, okay, and then you summarize, find the largest people with find the person with maximum cholesterol and the minimum cholesterol. Okay, so that's you can see that for each diagnosis group, you can see the largest cholesterol and the smallest cholesterol. Find the largest and smallest cholesterol for each diabetes diagnosis group and by age group. So this is where you can actually, the group by, you can have multiple groups. Okay, so you can order by multiple groups. So you can order by the diagnosis as well as the age group and then find the same thing, right? So if you do that, it's going to give you a good table with diabetes, the age group, and what's the largest cholesterol and the smallest cholesterol content, right? I mean, it's going to give you both by age group and diabetes. It's going to automatically trying to do. You can find the mean, you can find the, median, etc., whatever that you want to find. So grouped variables can be, I mean, grouping variables with summarize can be very powerful. It can give you lots of insight into the data, but you can also use it with mutate and filter function. Okay, so for instance, this is an example. Among the diabetes diagnostic group, find the top 3 ranks with high glucose levels, right? So what you do is this: I take the Haynes, I group by both the diabetes and the age group, and I find the rank, the top 3 ranks, and then I select. This is just for showing purposes. Just select those columns and then I arrange it according to the descending order, right? So this is what you see. So it's going to find by the age group and the diabetes diagnostic status, and it's going to give me the results for each, the top 3 diabetes information in there, top 3 glucose information in there. Find age groups greater than a threshold and standardize. And this could be very important. Like for instance, if you're doing some complicated statistical modeling, right? You may want to standardize according to the values that you find in group. So this can be useful to do that. For instance, you have what I'm doing here is I'm trying to group by the age, counting the number of people in any particular age, and I'm taking out all those people who are greater than, I'm taking all the groups where the people's number of people is greater than 30. Okay, so that's given by this, and then I'm trying to find standardizing A1C, that's the hemoglobin factor, right? Hemoglobin content. By this standardized A1C equals A1C divided by the sum of A1C. It could be some divided by some normalizing factor, it doesn't matter. But the mutate lets you make this new transformation of standardized A1C, and then you can plot it or you can observe it, right? So what it does is it takes the number of people in the group, takes the A1C variable, and then it divides it by the total number of the values in there, and then it's going to give you a standardized values, right? So these are some of the things that that you can do with this transformation. I mean, it's going to be really critical. So for this, I did not assign any project or homework as much as I did last time, because you are going to do all of this as a part of your project. So I think the homework 4 is, is the midterm project assessment for the final project. So if you go to homework 4, you have to apply the explore and wrangle paradigm to the data of your choice and submit the results. So you're going to take any of the data sets of your choice, apply these transformations and find some insights, see how things are, I mean, it could be some interesting information that you could find. I mean, it could be any data, like, it's not it need not be restricted to the data that you find it here. There is a big data set that's available, medical data set that's available here, right? It's medical imaging. Have you ever looked into these data sets? So you can look into congenital heart diseases. I mean, whatever that your research, if you might be doing some research in microbiome data, and Johan, he is working in microbiome, so he can help you analyze some of these data sets, right? I mean, or some of these. So feel free to take, or you can take a genomics data set. You can take a gene expression. It's a perfectly good data, right? And then try to find out some information about how genes are performing, right? I mean, some variables, some directed insights based on this transformation. All right, so that's all for today. So I'm going to